right, your left, I guess, of that square over there, get scanned in. You can get 50% off of your subscription as well. So if you're CML curious, then we can then that's a great place for you to go there. But with that, I got the go ahead from Emma. So we're going to start. Introduction to Kubernetes. For those of you, just before you started, show of hands, how many have actually used Kubernetes before at all? You kube-cuddled at all? Okay. How many are familiar with Docker? Have you run containers? Have you done Docker Compose? Okay. If you thought Docker Compose was confusing, buckle up, because it's only going to get worse from here. My name is Quinn Snyder. I'm a technical advocate with Cisco Learning and Certifications. I help with the CiscoU platform writing tutorials, but I also do things like the leaderboard for the Indy race simulation we've got. I do these presentations. I'm here. I'm in the DevNet zone. I do certification breakouts. I'm everywhere. You can find me on socials at Q Snyder, LinkedIn, Twitter, and if you really like shallow and incomplete code, my GitHub is also at Q Snyder, and feel free to leave a comment about how bad my code is. I don't know if this is going to be in the WebEx app for the slides because we didn't have to go through the process, but no fear. At the end, I will have a QR code where I will take you to the GitHub repository, which has all the code I've used as well as a PDF of the slides, so you get the full experience, for better or for worse. So we're going to talk about Kubernetes, some fundamental components, and then how to lab Kubernetes without having a massive cluster or buying a bunch of Raspberry Pis. I'll do a little demo to illustrate this. It's not very difficult at all, just talking through some of the components of what makes up Kubernetes when you deploy a cluster, and have the code there, and then we'll wrap it up. So Kubernetes, everyone knows, cloud-native project, started by Google, released in 2014. It has now been accepted into the CNCF, so the Cloud Native something or other foundation, Cloud Native Computing Foundation project. So it's no longer owned by Google. It is now a completely separate entity in and of itself. And it was originally meant as a platform for the stateless deployment of container images and managing their lifecycle. Now, keep in mind, it's just managing the life cycle, and we'll get on why that's important in a little bit. The other reason I say is stateless is originally it was just running containers. Containers are stateless services, microservices. We integrate things with APIs. Once the API request is done, we don't care if we hit another container. We don't storing state. We don't have databases. We don't have anything like that. That's changed a little bit, and again, I'll talk about why that's important. But stateless, microservices, and lifecycle. The thing that I find the most intriguing and cool part coming from the DevNet side is that it's API driven. So when we talk about using kube-cuddle, that's actually just interrogating an API. So we have a control plane container that runs. That API gets interrogated by that kube-cuddle application, but we can do that from anywhere. We don't need to be on the local host. We could do that remotely from our workstations if we have that configuration generated. And of course, support amongst so every major cloud native provider, AWS, Azure, GCP, all the other clouds, Oracle, they all have some flavor of Kubernetes, which if you're doing it at scale, I highly recommend. And again, I'll touch on that in a little bit. So it's really just Docker all the way down. So yes, now they've moved over container shims, but it's just a bunch of containers. So we have these things called nodes. Those nodes are running the baseband OS, usually Ubuntu, although Red Hat works as well. On top of that, they have this control plane for the container runtime. That used to be docker.io. Now it's containerd, which is not quite Docker, but we associate containers with Docker, so I'm going to conflate the two intentionally. And then on top of that container runtime, we have these applications that run, app A, B, C, D. I call them apps for a reason. Normally, we run an application per container. So I'm running a web front end. That's its own container. I'm running some middleware application. That's its own container. So we have these apps that run on top of that are integrated with the container runtime. And then we have certain access via sockets to the kernel space. So from a container, I can map to a volume on my local system if I choose. So if you're running local containers, and I talk about using containers for development purposes in another CiscoU session, you would use that shim there. When I interact with Kubernetes, I'm not interacting directly with each of those individual nodes. Over top of this, I have a platform umbrella called my API control plane that I use to interrogate. I could do raw curl commands to those APIs, or more commonly, I'm going to use kube-cuddle or something other like that interrogates the API based on my configuration. I'm not going to be using like Docker CLI or anything like that to do any work on there. Like I said, we can run kubectl from any workstation that we choose. So this is an actual picture from the Kubernetes website. So kubernetes.sig.io or something like that. This is Kubernetes. This is the basic fundamental architecture. We have this control plane that's its overarching umbrella, 2 individual nodes, and that's it. So we have a control plane which does not run any workloads. It's just communicating with those nodes. We stand up our control plane. Those nodes get joined to the control plane via a certificate and some configuration to say, you as a control plane can now work with each of these individual nodes. We do that manual join process. That control plane only manages the API, the scheduler, and resource management. Again, just those 3 things. The control plane is not a node, and the nodes are just grunts. If you go to the Kubernetes docs, it says take a node, remove all swap, basically make it as bare bones and dumb as possible, so we can run as many containers as possible, so we can maximize that. The status of that node is reported back to the Kubernetes control plane, so we don't overextend that individual node. But we don't want the node to outsmart Kubernetes and push stuff to swap if there's no RAM, et cetera, et cetera. So this is an eye chart of terms. These are the base fundamental pieces. We have clusters, that's just a set of nodes and a control plane. A deployment is an individual release of an application to one or more nodes. We have these things called namespaces. And the namespaces are almost, if you're a Kubernetes professional, you're going to laugh at this, but for all networking purposes, think of a namespace as like a VRF. It's just some place where we can isolate the types of deployments separate from each other. So there's a bunch of namespaces that are installed by default. We can have overlapping names across namespaces, but we can't use the same deployment name within a namespace. So generally what happens is when we deploy an overlay networking, or we deploy storage, or we deploy our underlay, all of that will be done in separate namespaces to keep them unique, just so there's no collisions. We talked about nodes. It's our worker machines. A pod is a set of running containers. So when we talk about individual pods, we'll see one or more instances of that pod being spun up based on the replica sets that come with Kubernetes. And then a service is just a method for exposing something external out of our cluster. By default, if you've played with Docker before, we know that Docker runs in its own little space. It does not expose itself outside of the host. Like we have to do an expose on our Docker file and then map that to ports on our local host machines. Same thing with Kubernetes. Kubernetes runs in its own little isolated world, and to expose those services running in Kubernetes external to that cluster, we need to have services. So I'll touch on that in a little bit with our demo. Now, I emphasized a little bit, or a lot, about what Kubernetes is at its base. It's API, it's resource management, and orchestration. That is it. So, additional things that are nice to haves. Overlay networking between pods. Persistent storage. Observability through Istio or Callisti. All of that is an add-on to Kubernetes. Now, what makes that really interesting is if you've ever seen the CNCF like world map, there's like 3,000 different projects that are under the CNCF that work with Kubernetes. It's intimidating. Now there are some leaders, you know, for storage we've got Rook and Ceph. For overlay networking we've got Calico, we've got Flannel, we've got Istio for observability, and then people build sidecars on top of Istio. All of those things though are separate. So what happens is when you as a network engineer install vanilla K8s, you go, why does this not work? Why don't these things happen? It's because they depend on these other pieces which you have to install by yourself. Every engineer should exactly once build up a Kubernetes cluster from scratch. And at that point, you will understand the power of cloud and abstraction. So it's an exercise left of you. You guys can do it if you want. But to understand the value of cloud and why cloud is very powerful, build up Kubernetes. So you have to install Docker. The Docker version has to be compatible with the Kubernetes version, which has to be compatible with your overlays, which has to be compatible with your distributed storage. Like all of these things are all dependent and have specific version requirements. So you do it once, and then you say, I'm never doing it again. I'm leveraging AWS. So without having to go through that cost challenge with things like AWS, there are various local Kubernetes tools. So there's MicroK8s, which is from Canonical, the same people that brought you Ubuntu. MicroK8s.io. It's a lightweight, like it can be used for testing, but it's also deployed for like low power hardware at the edge. Minikube, which installs a single application that mimics Kubernetes, and the advantage of that is you can work beyond Kubernetes SKU. So by default, Kubernetes has an N-2 support strategy. So current version, 2 back, that's all that they support. You can run ancient versions with Minikube if you choose to. My personal favorite is Kind, Kubernetes, and Docker. So I spin up Docker nodes that mimic Kubernetes nodes that then form all the overlays on top of that, which makes it really nice. There's a little bit of inception going on, and it makes it difficult to do some things. But it's a really good tool, and I'm actually going to be demoing in Kind today. And then I have Docker Desktop, which you can use if you want, but usually the nice thing is if you have a PC running Docker Desktop, you spin up a Kind cluster, you can change the context to that Kind cluster, and everything's good to go. Production implementation. So we can use MicroK8s, we can use K3s if you're doing some lightweight bootstrapping. K3s is a really good tool. On a Mac, you can do K3D, which is a daemon on top of K3s, which makes the deployment even easier. OpenShift, or pick your own cloud provider. And obviously, cloud provider is one of my favorites because you don't have to worry about anything. They just handle it all, and you deploy a manifest, and you're good to go. Or you can roll your own. And you notice there's something in between there. You can do anything else. Just don't roll your own for production. It is absolutely awful. And for a little bit of a selfish plug, Chapter 7 of the DevCore OCG, which I wrote, covers Kubernetes and clouds. We can talk a little bit more about this if you want to dive into it a little bit deeper. So, my demo. This QR code will take you to my repository of really, really bad code. But if you want to save it, it's just QSnyder. If you go to my GitHub board, QSnyder, and then CiscoU 2001, search for it, you can find it, but that QR code will take you there as well. And now we will jump into a demo. So in order to do this effectively, I am going to I'm going to talk through this while I run what's going on here. Assuming I have internet connectivity, please tell me I didn't die. There we go. Okay, so in the repository, you'll see a couple of different files. One of them is this Terraform plan. Don't really know a whole bunch about it. I have a document, or I have it documented in the README how to use this. But in this case, I'm spinning this up in AWS EC2 just because of the resource requirements. You can, if you have a beefy workstation, you can do this locally. If you have a server, you can run the same thing, just change the targets. But this is going to bootstrap this entire thing for me. So what I'm doing is I'm creating an EC2 instance, and again, all this code's provided. Creating an EC2 instance that's going to stand itself up, install Kind, and all of the dependencies, copy over some prerequisite files that are also included in the repository, and then hopefully this all works. I should have done this beforehand. But all that will be provisioned. And there we go. Okay, so we're still creating. Hopefully my provisioner is working. Okay, yeah, we're coming along. Okay, so like I said, this is going to go through. It's going to update some packages. It's going to install Kind, which it requires some Docker installation. And then there's going to be a tarball.gzip, which is also there and decompress, which is going to has the Kind files as well as the application manifest for SockShop. So if you're not familiar with SockShop, it's a microservices application developed by a company called Weaveworks. They used it to test their own microservices, and then they open sourced it and released it. It's kind of like there's like a bookstore app and SockShop, and most of the open source demos around Kubernetes use one of those two, depending on how big they are. The nice thing about SockShop is it's fully functional, so you have like back-end databases, you've got search, you've got payment processing, and you have a web front end that you can expose. So it works out really well for demos like this. It is a little bit heavyweight, which is why I'm doing this in EC2. All right, sweet. So I am going to log in. So when you instantiate this, you'll see that we have this folder called demo. And I am going to, let's see here, CD cluster. We have this cluster build command. So if I just cat cluster build, we're going to stand up a kind cluster. So this is really just saying we're going to name it demo, and we're going to point to this config called kindconfig.yaml. If I look at kindconfig.yaml, you can see that this is where we're building our cluster. So we have a control plane node, and I've got 1, 2, 3 worker nodes, and I'm disabling the default CNI for a reason. That's the overlay networking that goes on inside of Kubernetes. So if I just bash, was it cluster build? We're going to build our kind cluster. So this is, and you'll see that the output from this, we're going to download the node image. So this is actually running in Docker. It's going to prepare the nodes, so start them up inside of Docker. And then it's going to do all the fancy things that I talked about. It's going to build some overlay networking, even though I disabled it. It'll just like skip over that part. It's going to build permanent storage. So if I needed to run permanent storage applications, I have those PVCs ready and to go from a storage perspective, and make sure that everything is all ready to go so I can interact with this cluster immediately. It's also going to build my kube config, which is the configuration to use kubectl to talk to the cluster. So there's an IP address target, but then there's also a hash that gets generated with every kubectl config that says, if you don't have this certificate, you can't talk to this cluster. And I'll show that in a second here. So we've started the control plane, installed the storage class, we have PVCs. Now we're joining the worker nodes. We're saying each of these distributed Docker clusters are going to join to my control plane so we can work with them. And once that's done, everything should complete. Oh, Amazon is not working fast on a Monday. There we go. So now, so kind has its own, is there kind get kube config. So when I talk about a kube config here, this is what actually gets generated. So we have this entire certificate authority. We have our address, so that's where that API is listening to on our Docker cluster. And then we have the context behind that as well as the certificate data. If I don't have this exactly, I can't talk with the cluster. So there's some security built in there. You just can't be some guy who, I'm going to randomly start pinging the internet for open Kubernetes clusters. Although there was a security breach a few years back where someone had it exposed, and it was bad news. Just to show you that there's nothing up my sleeve here, if you run a Docker PS, we can see that we have those 4 containers running. And then you can see based on the ports that we have that same port 38557 is mapped to 6443 internally. So 6443 is like the default Kubernetes API port. We've just exposed that API container is running that port. We expose that to some ephemeral port externally on the local host, so now we can communicate with it. So everything is up and running. Now, anytime we want to interact with our cluster, we're going to use kubectl or kubectl. There's 1,000 different names. I'm going to call it kubectl. So we can look at each of our individual pods. Now, if I do kubectl get pods, it says there's no resources found in that default namespace. That's that separation that I talked about earlier. This whole thing is up and functional, but because each individual piece is put in its own namespace to separate it from everyone else, you have to make sure that you either include all namespaces or define a namespace in and of itself. So if I do kubectl get pods -a, that says give me all namespaces. We're not going to filter. So you can see I have 2 different namespaces that were deployed. The kube system, which has our scheduler, some proxy stuff, which you'll see in the slides as well, our controller managers, our API server, and then our control plane. All of that's running inside of the kube server there, as well as that core DNS. Now you see that those are pending. I disabled the overlay piece. So Kind is going to create some DNS listeners so I can find these microservices inside the clusters, but they can't communicate with each other, so it can't bring up that DNS service. I have to enable something to do that. And then we also have this local path storage, so I have the ability to store stuff within my Kind cluster if I choose, so we can mimic actual applications. So now we're going to get back out of here. There's a few other pieces that I have here. So I'm going to install Tigera, which is the Calico networking overlay. So there's 2 pieces I'm going to do here. I'm going to apply the Tigera operator as well as some custom resources. I won't show the first one because it's really big, but you can. Everything in Kubernetes is going to be written in YAML. So it's just a YAML configuration file. All this is saying is enable VXLAN cross-subnet communication between these nodes using the Tigera operator that we put together. So it's going to build all that overlay networking for me. Some of these manifests will get really big, and it seems intimidating to look at them all. They start repeating a pattern, you start picking it out, and you can look at some of these later on in the actual repo when you have a chance. So I'm going to do kubectl create -f, which says point to file, Tigera operator. So it's creating all of these new custom resource definitions inside of the cluster, and I'm going to also do the same thing with custom resources. Okay. Now, if we do a kubectl get pod or get pods A, we can see we've added some new pods to a new namespace, Calico system. So that Calico networking overlay has now created itself because of that custom resource definitions we've created, and it's initializing these. And we can see that once these actually initialize, that core DNS will now be up and functional. And it's running slow, but we're slowly creating these things. So right now, it's just creating all of those different node drivers to integrate with all those different pods to allow that overlay communication. Okay, so we're almost there. But we can see now that core DNS is up because we have that overlay now functional. Again, because if I wanted to do, I could just do a get pod, say n, and we could do cube system. We're only going to get the cube system. So you can define what namespace, or you can look at them all. So we've done that separation. Now, same thing if we want to look at deployments. Just to talk about the difference here. Deployments. We don't have anything in the default namespace, but if we do deployments -a, we can see that we have each of those individual deployments. And if you notice a pattern here, each of these deployments has a name that relate to the pods that are up there with some extra stuff on top of it. So we have like this core DNS deployment inside of Cube System, where we have core DNS, and then we have like this weird stuff appended to it. So it's tracking, it pulls that deployment name, applies it, and then adds something to make that unique so we don't have collisions inside that namespace. Two pods cannot be named the same thing inside of a single namespace. You'll get those collisions as well. So just, you can kind of determine what we've installed and then how those individual pieces are running. Great. So now we have baseband Kubernetes up and functional. I know I'm running short on time, Emma, so just give me 1 second. So now I'm going to deploy this sock shop. And we're going to do kubectl apply f sockshop.yaml. So this is actually going to deploy the sock shop application. You can see there's a lot of deployments that were created. We've got carts, a database, we've got a catalog, a front end, orders, and all this other messaging bus that goes on between these containers. If we go back to get pods-a, we can see we've got a lot of stuff that's being built, and that spun up really quickly, almost freakishly so. Now, one of the pieces that let's see here, maybe make sure I copy this out here correctly. So this is supposed to be able to be copied. Actually, let me take that back. I need to, so because we're running inside of a cluster, instead of EC2 without ELB, Elastic IP, I needed to expose these services. So I'm going to bash this caddy command. So this is going to say we're going to be listening on this port 3001. Now, just to show you the power of the services, I've copied that URL over. Nope, not Edge. Let's go. Come on. Chromium. So I copied over that URL, which is my running EC2 instance. And if I attempt to access it on port 8080, I can't reach anything. So it has a front end, but I have not enabled it. So talking about services, and I'll do this real quick as a wrap up. If I cat the sock shop node port, we're exposing port 3001 to port 80, which is our front end service, which is running in those pods. If you want to go back and check this, you can check it on later. And if I was to do a kubectl get services -a, I've got a lot of these cluster IPs, but nothing exposed externally to my cluster. So I'm going to apply this node port. I created this, and now you see the difference here is I've created a service instead of a deployment. So I have this new service running. And if I look at my services, I now have this node port, which it has a mapping just like I would in Docker, mapping port 80 to port 3001. Now, Caddy's exposing 80 to 8080 to do the reverse proxy stuff. So now I should be able to, I might need to redo the Caddy command. Please don't fail me now. Oh, you know what? Let's do this. That's why. I need to fix that in this repo. There's a missing C. And now, in theory, we should have Murphy. Okay, take my word for it. This should work. And if you pull down the cluster itself, I'll leave this up to see if it comes back up. Like I said, the repository is available. I'll pull up that QR code again. Please fill out surveys. Make this any better. I know this was rough. This is supposed to be working. I don't know why it's not working. I will post proof with a screenshot and time in the repository. You can see I wasn't lying, as well as what I did to fix it. Fill out your surveys, continue your education. We've got CML, we've got CiscoU, all these kinds of things. One last thing I want to touch on is underneath one of the seats, there will be a ticket that is taped. So if you're sitting in a lucky seat with the ticket taped, you will have the opportunity to win something. And with that, I'm gonna disconnect and do everything. If you'd like to talk to me more about Kubernetes, please come find me. I'll be around all week in the CiscoU theater. I'll be doing some breakouts. I will also be doing a session on Docker, Terraform, and a bunch of other goodness. So thank you so much for your attendance.